Okay, so
So what? So what, Berg? Please don't kill me.
I'm going to die.
If the video's on, so we.
I'll say it's recorded, and so if I do kill you, I have it on record why I killed you.
I'm
And
sure
your mom and dad would go, "Yep, he had it coming."
Yep.
Makes
No,
sense.
no charges would be pressed.
Oh, absolutely not.
Makes sense.
Absolutely not.
Like,
Okay,
yeah, he's gone.
so today is a good news, bad news day.
No.
Yes. So going into the weekend, you don't have any homework, so that's so. Now,
It's just a good news.
yeah.
It's a very good news.
Yeah.
Everything else is.
So, and the other good news is we'll do some cool demos today. So, we're going to start this unit on forces. So, you kind of got to start with just what a force is defined as in terms of a physics class. So, and it hinges on one word, and that's the fact that a force is capable of causing an acceleration. It doesn't necessarily mean that it's going to, okay? It's capable of causing an acceleration. So, when you look at motion, okay, and you kind of have to weave two different ideas together. So on the back side of the lecture notes that I just gave you, there's Newton's 3 laws of motion. And even those have to be taken in conjunction together. So the first law of Newton is what's known as the law of inertia, okay? So inertia is the resistance an object has to undergo a change in velocity, okay? And there is only one thing, and one thing only, that determines the amount of inertia an object has, and that is mass. The more stuff there is, the harder it is to get it to move. But once you get it moving, the harder it is to get it to stop. So here's the classic example. So I've got Gary the golf ball, and I have literally Hank, okay? This says Hank, right? The bowling ball, okay? Hank just showed up. I came back from summer break. This is maybe 10 years ago. And Hank was in my room. Like, somebody decided that I needed a bowling ball. So I
Of
walked
course you
in,
did.
on my desk, there was a bowling ball. I did add the I to it, okay? So that wasn't part of the standard issue, Hank. So Hank obviously has a lot of stuff, okay? Go to the golf ball, not so much. So what this means is that I love you all dearly, but I'll take my hand and I'll drop Gary the golf ball on it. Not a big deal. I am not going to do the same thing with Hank. Why?
It might
Your
hurt.
hand
Mike?
Because there's more force.
Yeah, Hank has more stuff,
Hank will
right?
kill.
Hank has a lot of stuff, so that takes a lot more force
On the hood.
to stop Hank than it does Gary the golf ball. So force, in some ways, equals pain, okay? The more force there is, the more pain there is. So, here's the story. So if you look at Hank, it's very difficult to get Hank to move, okay? Hank has a lot of inertia. Hank has a lot of stuff. But once you get Hank moving, it's hard to get Hank to stop. So when you look at inertia, and I emphasize this again, it is only dependent upon mass. If I take Hank to the moon, Hank has the exact same amount of stuff. Hank is going to have the exact same inertia on the moon as he does on Earth if he was in the International Space Station, if he was on Saturn. Doesn't make any difference because it's a measure of stuff, okay? Now, you talk about weight. In a physics classroom, listen to me. When you talk about, for example, Newton's second law that says F equals ma, he got very verbose when he wrote this out and said, oh, the amount of force imparted to an object is directly proportional to the acceleration, and it's just F equals ma. But here's a caveat, and we'll talk more about this later. This is technically what's known as the net force, okay? So the net force is gonna be an imbalanced force. So here's the classic example. This is what we talked about yesterday. So this apple on Earth weighs 1 Newton. So if I hold this up right now, there's forces acting on it. The strange rock that we're on has a gravitational field that's pulling it down. My hand is exerting a 1 Newton force going up. So this is the classic quintessential example of, hey, I have forces acting on an object, but I'm not accelerating. So one of the first things I want you to get out of your minds right now is that every time a force acts on an object, there's an acceleration, okay? Cohen is sitting there in his chair, right? Okay? Gravity is trying to pull him down, okay? But he's not accelerating because the chair conveniently is providing a normal force, we call it normal force, which we'll talk about normal force later. The normal force is what's being provided by the chair and the floor. Now, Will wouldn't do this, but let's just say, Will walks up behind Cohen and grabs the chair and pulls it out from underneath him.
What do you mean I wouldn't do this?
Just stay with me, I'm giving you the benefit of the doubt, okay?
There's no doubt.
Immediately, what's Cohen gonna begin to do?
Fall.
Now you're gonna begin to accelerate, okay? Because now you have an imbalanced force. So rule number 1, when you look at net force equals mass times acceleration, that net force is only if there is an imbalanced force. Every force does not cause an acceleration, okay? Now, the third law says that for every force, there is an equal and opposite force, okay? Sometimes this is referred to as forces being coupled. So again, here's the classic example. I hold up this apple. The earth is pulling down on the apple with a force of 1 Newton. The apple is pulling up on the earth with a force of 1 Newton, okay? Listen to me, I hit my hand on the table. I exerted a force on the table. What did the table do?
Exert a force on your hand.
Exerted a force up. I'm going to jump up in the air. Did I exert a force on the earth?
Yeah.
What did the earth have to do?
Exert a force on you.
Exerted an equal and opposite force. Now, this is where the law of inertia comes into play. I let go of this, the apple begins to accelerate towards the earth. Why doesn't the earth accelerate upwards towards the apple?
The earth has
Much
a lot
more
inertia.
mass.
Yeah, has a lot more mass, has a lot more inertia, okay? So even though there is a 1 Newton force acting on the earth, thankfully, when I let go of it, it isn't like the earth begins to move up and they meet halfway in the middle, okay? It's like, oh man, somebody dropped a pencil, boom, okay? No, it's cool, okay? It's cool that that doesn't work. But listen to me, listen to me, listen to me. For every, and this is sometimes it's called action-reaction. For every action, there is a reaction. And sometimes we'll have what we call contact forces. So, and typically that's how your life plays out. Because let's say you want to pick up your shoe in the morning and put it on. Okay, you are going to grab a hold of the shoe. It isn't like you can put your hand over the shoe and then like summon a force and have the shoe lift up towards you.
Dang it.
Cool, don't get me
That would
wrong.
be sick.
Okay? But that's not gonna happen. You want to write with your pen. Okay, you've got to grab a hold of the pen. Okay? You want to lift up your book. You've got to grab the book. Okay? Those are all contact forces. Sometimes, rarely, you have non-contact forces. So let's say, for example, Cohen is standing on top of the table and he jumps off.
Should I?
No.
Okay.
Now, is Cohen going to begin to accelerate? Yes. But there's no direct contact between Cohen and the earth. Now, there was for a while, they viewed gravity as being magic, okay? And here's why. If I put my hand like this, and I drop it, and the ball falls this way, everyone goes, oh, it's gravity.
Yeah.
Do you see any causation, a visual causation, any contact forces, that you actually make the apple move? No. So you go, oh, that's gravity. Now, if I were to let go of this apple and hold it like this, and that apple began to accelerate upwards, you would go, it's magic. So if it falls this way, oh, that's gravity. If I let go of it and it goes up, that's magic. But in both situations, there's no noticeable force acting on the apple. But in one situation, oh, that's the law of the universe. The second one, Bergkamp's the wizard, and that's burning at the stake. Okay?
Let's burn at the
That's
stake
kind of the
anyway.
difference between the two stories. So this is why for a while, gravity was viewed as magic, because there's no visible causation to make something move. Okay. Now, you also need to view science through a historical lens, okay? So, Newton published his work in the late 1600s. Some say that he borrowed some work from Galileo, which he kind of acknowledged, because if you look at what Newton said, they said, hey, what allowed you to come up with all this stuff? And his famous quote was, the reason that I have seen so far is because I've stood on the shoulders of giants. So he kind of acknowledged that, hey, I just kind of took a lot of ideas that were already out there and just kind of synthesized them into one big idea, okay? And he acknowledged it. He goes, some of the stuff I just took from other people. And that was kind of his shout out. I stood on the shoulders of giants. So that was late 1600s. Now, there was a whole bunch of other things that were going on at the time. Wars, bubonic plague. It was not a good time to be alive. There were no Oreos, there were M&Ms, anything like that. It was not a good time.
No reason to live.
So, but one of the things they struggled with is like, how do we classify this stuff? Because scientists like classifications, okay? Like the biology department has like phylums, kingdoms, whatever that whole thing, Ponzi scheme is, okay?
Yeah,
So
that's pretty accurate.
yeah, it is. It's a Ponzi scheme. And so they like classifications. So the physics department said, you know, the chemistry department has a periodic table. They arrange stuff like that. Maybe we should do the same thing. So they got together and said, okay, what can we come up with? Well, let's call them fundamental forces. So initially, there were only two fundamental forces. Obviously, one of this is gravity. Now, we're going to spend a lot of time talking about this equation. This is just the opening salvo of this equation.
Uh-oh.
So to calculate the gravitational attraction between any two objects,
Uh-oh.
you need big G. Don't worry about what big G is. Big G is just a number. M1, M2 over D squared. Okay? So here's the significance of this. Big G is what's known as the universal gravitational constant. It's a number, don't worry about it. We'll get to it. Okay? Just know that it's a number. Here's going to be your two masses that are going to be multiplied together. So obviously, as the mass gets bigger, what's going to happen to the gravitational force?
It increases.
It's going to increase. Now, you're going to divide by d squared. So as the distance increases, what happens to the gravitational force?
It exponentially decreases.
It exponentially decreases. So one way you can show this, and I'll pass this around just because it's cool. So this is called ferrofluid, and this is a pretty strong magnet. Don't get, not that your phones are, but don't let it near your calculators. So when you bring this near, you'll see that the ferrofluid arranges into spikes, okay? And the closer you bring the magnet, the closer the spikes become. So magnetic fields are also an example of this inverse square law. So this is just a cool visualization. It's kind of like gravity. So, but because it gets, this is not a technical term, but it'll make sense once you see this. So the ferrofluid gets spiky, okay? It isn't a continuum. It exists in spikes. So what that means is that the magnetic field, unlike the gravitational field, which is a continuum, a magnetic field exists within specific lines. It isn't a smooth continuum around the magnet. So that's, if it was, then when you did this, it would form just a smooth sphere. But because it's spiky, which is again not a technical term, that tells us that the magnetic field is not a continuum. It exists within defined regions. So I'll pass this around. It's just kind of fun to play with. Now, when you look at everything that had to happen for us on Friday, September 6th at 8:05 and then G20 on this strange rock orbiting an average star and a star that's orbiting kind of an average Milky Way galaxy that's traveling through space. There was a whole bunch of things that had to happen just right for us to be here. One of those is the fact that gravity exists, okay? Thankfully, we live in a universe with gravity. Doesn't have to have gravity, but we did. So, if you go back 14.7 billion years, give or take about 10 minutes, something happened, okay? It's called a singularity. We don't know exactly what happened. But the short version is that everything that exists in the universe, everything, me, Danny, every atom that makes up Saturn, the Earth, everything in the universe was in one infinitely dense spot. Something happened. We don't know. And the universe came into existence as pure energy. And then even within that, it's a good book. It's called A Brief History of Time. And it kind of goes through and takes you through the origins of the universe and what we think happened. You've got this region of hyperinflation, and the universe expanded and it cooled. And you can kind of model how that happens. So if you take your hand in front of your mouth and you blow on it with your mouth open like that, it feels really warm. But if you pucker your lips and blow on it, what happens?
It's cold.
It feels cool, okay? Because it's expanding, and as it expands, it cools. So the universe, okay, stop, that looks really weird. Okay? So, as the universe cooled, it expanded. Now, part of this equation or story is E equals mc squared. Okay, Einstein's famous equation that relates energy, mass, and the speed of light. We'll spend more time talking about this. So basically, what this equation tells you is that the door can swing both ways. You can take mass and convert it into energy, or you can take energy, pure energy, and get mass to appear out of it. That's conceptually tough to get. Converting mass to energy, that door swings pretty easily in our mind. But the idea of taking pure energy and having mass appear out of pure energy, that's kind of tough. Because obviously it isn't like I can just clap my hands like, oh, if I clap my hands loud enough, I'll get a proton to appear. Okay? No. Okay? It's a lot of energy. We've done it. We do it all the time. That's how we make antimatter. Okay? Like, antimatter is like called a positron. So a positron is just like a normal electron, but it has a positive charge. Okay? And you can have negatively charged protons as well. But the problem is when you have matter, what we're used to, and antimatter, as soon as they run into each other, they annihilate each other and turn back into pure energy. So this is why you're like, oh, I want an antimatter, laptop for Christmas, okay? It's not going to work. Because even if they could, as soon as you would touch it, bad things would happen. Because it would basically turn back into pure energy, and so would you. So I don't recommend that. Yeah, gone. What happened? Ran into this man and matter on the way to school. Bad things happen. So when you look at how the universe began to form, and this is a whole line of study, but I'm going to give you a very condensed version of the universe. So the universe began to cool. Out of that energy, once it cooled down enough, then you begin to get matter. Okay. Initially, the periodic table was very simple. You had hydrogen. Okay. You had a proton and an electron. That was it. Okay. That was it. Might have had a little bit of helium, maybe a trace of lithium, but that was about it. The universe existed as hydrogen. So as that began to spread out, because space and time was being created as the universe expanded, then eventually you got disturbances in that space and time. It wasn't a homogeneous distribution of energy and mass. If it was a homogeneous, completely homogeneous distribution of energy and mass, we wouldn't be here having this discussion, because there would not ever be gravity that would form the stars. So thankfully, there was variations in the density. And gravity creates gravity, because as the hydrogen began to stick together, that increased the mass. If it increased the mass, that created a stronger gravitational force, which pulled in even more hydrogen. So there were no stars at the beginning of the universe. So eventually what would happen is that you would get enough of this hydrogen gang together, and they would start a star. Okay, a star is born. And so if you could be an outside observer in the universe, you would begin to see flashes of light as these stars began to turn on. But that was tough. It is like, oh, we'll make a star. Cool. Okay? So the problem that you're fighting, and this is the electromagnetic force, which I'll demonstrate in just a second, is that you had protons and you had electrons. Well, the protons didn't like each other because they had the same charge. So to make a star, you had to have extremely high temperatures and extremely high pressures to force the hydrogen to smash together with enough force that you can make helium. So as helium is formed, if you look at this equation, E equals mc squared, the helium that's formed has a slightly smaller amount of mass than the hydrogen that it originated from. But you're multiplying that by c squared, which is the speed of light, which is 3.0 times 10 to the 8th meters per second. So you square that right away, you're at 9 times 10 to the 16th, okay, which is a big number. So it doesn't take very much mass to produce a lot of energy. So you have these first generations of stars, hydrogen is smashing together with helium. You're seeing flashes of light begin to appear in the universe where these stars have been formed. We're not part of the story. Okay, we're so far away from being part of the story. So then, eventually, those stars, short-lived, typically, they go supernova, they explode. We're still not, can't even be part of the story yet. So out of those explosions of those stars, that's when you began to form the heavier elements. That's where you began to get carbon, nitrogen, oxygen, all the way up through like iron on the periodic table. The big, massive stuff, like the gold, silver, that type of thing, that actually had formed from the collision of neutron stars, because it takes that much energy to make the heavier elements. So if you look at us being here, and it's a cliche, but the more and more I study science, and if you said, hey, Burkamp, what about science amazes you the most? Is the fact that all of the atoms that make up us didn't exist at the beginning of the universe. They were all formed in stars. All of that material got kicked out into just a huge disarray of material that got reef packaged into this strange rock. And out of this strange rock that's orbiting an ordinary sun, just the right distance, that's tilted just the right angle, and it's just the right distance from the sun, we're here having this discussion. Hello.
Do you have anyone who's filled out from a spare?
I do not.
Teacher. Okay.
And so that's pretty cool. The fact that we are all stardust, that all of the atoms, the hemoglobin that carries the oxygen in your blood, formed in stars. The carbon, the nitrogen, the oxygen, all of that was formed. And statistically, the atoms that make up this hand probably came from a different star that makes up this hand. Okay? They probably didn't even come from the same star. And so it's pretty cool that that got rearranged, and here we are talking about it. So philosophically, it's been said that humans are unique, that we are a group of atoms that know we're a group of atoms. So if you think about it, it's kind of cool. It's like a rock is a collection of atoms, but a rock doesn't know that it's a collection of atoms. It's a rock, okay? We're a group of atoms that know we're a group of atoms. It's kind of cool. So if you look at the strength of gravity, if gravity had been stronger, we probably wouldn't be here having this discussion. Because the universe might have expanded from the Big Bang, and then when it collapsed back on itself, and you would have had like the big crunch, okay? Been like a rubber band.
Forever and ever.
If gravity was weaker, we wouldn't be here having this discussion, because if gravity had been weaker, you would have never had star formation. In other words, you couldn't have pulled the hydrogen in with high enough temperature and high enough pressure to start the star formation. So the gravity is kind of in what we call the Goldilocks zone. We had enough gravity to create star formation, but the gravity wasn't so strong that it didn't cause the universe to collapse back on itself. So that's even kind of a cool thing. So the first fundamental force is gravity. Here's the only thing I want you to remember about gravity. Gravity is always attractive. Okay, you're not going to wake up in the morning and go to jump out of bed, and gravity is going to push you towards the ceiling. Okay, which would be cool. Probably not. If that happens, there's other things that are going on. So gravity is only attractive. The more mass that you have, the more force that there is, but the bigger the distance is, the smaller the force. That's all you need to worry about gravity for now. Now, the other force that they knew about is what's known as the electrostatic. So I'm going to do a little comparison here. So the gravitational force is m1, m2 over d squared. It's the number times mass divided by d squared. So that's gravity. Now, the electrostatic force is K, which is just a number, Q1, Q2 over d squared. Now, these Q's are charges. Okay, charge on an electron, charge on a proton, something like that. So, and this is why they think there might be what's called a grand unification theory. So if you look at these equations, that's a constant, that's mass, a fundamental property of the universe. This is charge, which is a fundamental property of the universe. And they're both inversely proportional to d squared. So like, that looks very similar. Maybe somehow or another these two are tied together. But the cool thing about gravity, and everybody thinks, oh, gravity is such a strong force, okay? You know, I drop Gary the golf ball. Whoa, it's immediate, right? But in reality, of all the forces, gravity isn't all that strong. And I'll show you a comparison. So Cone didn't have to give that a spin so we can look at this. So,
Balloon?
a balloon.
It's balloon.
So I got the balloon up there. I put my hand there. Now, does the balloon have mass?
Yeah.
Yes, it has stuff. Does my hand have mass?
Yeah.
Yes.
So is there a gravitational attraction between my hand and the balloon?
Yes.
Yes.
Yes. is it going to be very much?
No.
No, it's extremely small. However, I take a balloon and I rub the balloon, or take a blanket and I rub the balloon. Now when I put my hand there, now I can kind of do this Jedi trick, okay? And make the balloon move. Now, here's how I would explain how the universe works, is in terms of dogs, okay? So the universe, as you all know, is made up primarily of electrons, protons, and neutrons. There's more stuff than that, but those are the big hitters. So the electrons are like the chihuahuas of the universe, okay? They're small, they're yippy, they run around, okay? And they're annoying. So you got the chihuahuas, they're running around. They're the electrons running around. In the nucleus, you've got protons and neutrons. Those are like the St. Bernards and sheepdogs of the universe. They're there, but they're like, suck, okay? They take up a lot of mass. They're very densely packed together, but we don't move them. So chemistry is basically nothing more than the rearrangement of chihuahuas. Okay, that's it. Why is water H2O? Because oxygen has 6 chihuahuas, hydrogen has 1, they want 8 chihuahuas, there you go. Okay? So chemistry is just rearranging of chihuahuas. That's all it is. Okay? Now, once you begin to get into the nucleus, though, that's tougher. So if you look at a piece of aluminum foil, we'll use a piece of paper, it'll work. So imagine this is a piece of aluminum foil, okay? If you were to stack aluminum atoms side by side by side, it'd take about 94,000 atoms stacked side by side by side to get the thickness of one piece of aluminum foil. And but that in and of itself is pretty cool. But then if you look at scale, so if my hands represent the diameter of an aluminum atom, the nucleus would be the thickness of a human hair right in the middle. So of those 94,000 atoms, it's almost all empty space. And you simply go, that doesn't make any sense, Camp. This table feels solid. My hands feel solid. Okay? Tank feels solid. How can it be empty space? Because it's the interaction of the chihuahuas. Okay? Chihuahuas don't like each other. Now, so that's why this works. So my hand is made up of atoms. Atoms are consisting of the sheepdogs and the sheepdogs and the
St. Bernards.
the what?
St. Bernards.
St. Bernards. St. Bernards and sheepdogs. They are in the middle. I got a bunch of chihuahuas running around. So what happened, give this a spin. And we're going to do a lab like this in the spring when we get into electric field code. So when I rub the blanket on the balloon, okay? So the short version of what just happened is that the balloon took chihuahuas from the blanket. So the balloon now has excess chihuahuas, okay? So when I bring my hand close to this, the chihuahuas that make up my hand don't like the chihuahuas that are on the balloon, okay, because there's excess chihuahuas. So the chihuahuas in my hand go, yip, 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 and they're out, okay? They go running away. Like, they're out. Well, that leaves the St. Bernards and the sheepdogs that are there, because those can't move, because they're anchored. Now, the St. Bernards are positively charged, okay? So the St. Bernards, which have a positive charge, like those chihuahuas. So that's what makes that move towards my hand because those electrons, the chihuahuas, that you cannot see are running away. But the St. Bernards that are left behind go, we kind of like the little fellas, okay? I like them, right? So they're attracted to it. So that's why that moves towards my hand. Now, I take another balloon, not charged, okay? And I do the same thing where nothing happens because there's a complete balance between the number of chihuahuas and the St. Bernards. So this happens because of the fact that I have an imbalanced number of chihuahuas. That makes these chihuahuas run away. There we go. Now, but if I take and charge this balloon and move it towards that one, what happens?
It moves away.
It's repelled. Why?
Too many chihuahuas everywhere.
Hey, chihuahuas everywhere. So this is like a turf war between the chihuahuas, okay? That has excess chihuahuas. This has excess chihuahuas. They don't like each other. Now, here's the weird thing, amongst other things. Notice this is what we call action without contact, okay? There's obviously a force between those balloons, but there's nothing physically happening that we can see. So the electric field that does this is actually, and this gets really weird, because what actually makes this happen is photons. Can you think, oh, whoa, Burkamp, photons do light, okay? This isn't photons. It's like, yes, it is. The electric field is carried by photons. So now, is it photons that we can see? No, but there's a whole bunch of photons that we can't see, and that's okay. You get a message on your phone. That was carried by microwaves, okay? You can't see it because if we could see all forms of electromagnetic radiation, it would be like sensory overload, okay? Instead of like feeling that the stove was hot, you could see the stove emanating thermal energy, okay? You would see the microwaves coming inside the microwave if you could actually see them. It's cool that we only see a very narrow part of the electromagnetic spectrum. Otherwise, it would just be, you would see everything and it was like, oh, this gets really, really weird. But what's actually happening here is photons. That's weird. But then you can get into like virtual photons that pop in and out of existence. Now, here's the other thing that I'll tell you. And we'll spend time studying the quantum world in the spring. One of the last units that we'll do. But you cannot overlay a macroscopic idea of the world to what happens on an atomic level. Okay, you can't do it. Okay? We make the analogy, and we'll talk more about this later than just today, that like the nucleus is like the sun, and the planets that move around the sun are like electrons moving around the nucleus. And it's a visual, right? We don't know. We know the electrons are there. We don't know exactly what they're doing. Something called the Heisenberg uncertainty principle. If you try and measure where the electrons are, that fundamentally alters the existence of the system, and then you don't know where they are because you made an observation. Okay, so stop that camera.